Hello and welcome to this video tutorial on Spearman's row. This is one of our inferential statistical tests that we use in OCR A-level psychology. This is a test which looks at correlation, the relationship, the association between two variables. It's used when we have ordinal data, and it's quite a tricky one in some respects. It can be quite fiddly to use. So what I want to do is to go through a worked example with you. All right then, so the example that we're going to look at is this one here. So is a person's age in years correlated with their attractiveness? And the first thing we're going to do is to write a two-tailed alternative hypothesis for the study. So if you remember, with a two-tailed hypothesis, we don't have to give any direction. So in other words, we simply just have to say that we think there's going to be a correlation, there's going to be some sort of relationship between them. We don't say whether that's going to be a positive or whether it's going to be a negative relationship, just simply that there's going to be some sort of correlation. So let's see what we've put then. There will be a statistically significant correlation between a person's age in years and their attractiveness. Now you can see that that's two-tailed. Like I say, if it had been one-tailed, then we would have stuck in positive there or negative, etc. Okay, but in this particular case, we don't need to. That's a two-tailed alternative hypothesis. Now remember, with all of these, we need to have not only an alternative hypothesis, but a null hypothesis as well, because there may well be a chance that actually we end up with finding nothing here, that actually any correlation we have is just simply down to chance, that there isn't actually any association between these two variables at all. And our job when we're actually looking at results is to determine whether we can actually dismiss this null hypothesis and accept the alternative hypothesis. But this is kind of the default, I suppose, really, that we always go back to. So let's look at the null hypothesis. We've already done the alternative one. We've said here there will not be a statistically significant correlation between a person's age in years and their attractiveness, and any correlation will be down to chance alone. So what we're hoping for is, after doing all this, that actually we're going to be able to accept this one here, and we're going to be able to reject this one. But you know, that's not how psychology works sometimes. So let's see what happens. So what I'd like you to do then is just turn your attention to this particular table here, and just really focus in on the black writing. Just ignore the red writing for the time being. Okay, so it asks you to calculate the difference between the ranks of A and B, and then square these differences, and then add up the differences squared, etc., etc. Let's just make a little bit of sense of this table. We've got 10 participants altogether. We've got column A, which is age in years, and we've got column B, which is their attractiveness score. So you can see here we've got a wide range of different ages, going from 21 right up to 52, and then we've got column B, which is their attractiveness score. Now you'll notice here that it says score. There's no other way of recording attractiveness, I don't suppose. It's not really an objective thing, is it? This is purely a subjective judgment. So therefore it's not really surprising, is it, that this is going to be a score. This is one of the things that kind of makes this ordinal data as well, because this can be ranked, can't it? It's unsafe data. It's not actually been measured in any way, but it's further on than nominal data, isn't it? It's not just categories. These are rankable data. Okay, so what do we do now then? Well, if we can see here, we've got the same participant here, 52, 5, 36, 16, 47, 8. We need to do some ranking, and the first thing we do is we're going to rank column A. Okay, so column A is age. First thing we need to do is to work out what is the lowest score here. So who is the youngest? So we have a 21-year-old person here. Okay, they are the youngest if you look through that data there. And what we do with the smallest score, the youngest age in this particular case, is to give it the rank 1. Okay, so that's going to be our That's going to be ranked 1. Okay, it's the smallest score. The one with the highest score is going to end up being ranked 10. Okay, in this particular case, that's going to work out. Okay, let me just kind of go through that with you though, first of all then. So as we go through this 21, we can see that the next score up, okay, we have the next person here who's 25. They're going to be ranked 2. We've got someone who's 30. They're going to be ranked 3. We have someone who's 32. They're going to be ranked 4th. Okay. Then you've got a little bit of a problem. We've got someone who's 36, but we also have another person who's 36. We've already used rank 4. This person should be ranked 5, but we can't have 2 people ranked 5. You know, it doesn't quite work out that way, does it? So what we need to do is to rank them 5 and 6, and then divide 5 and 6 by 2. So add 5 and 6 together, divide it by 2. That will give you 5.5 and 5.5. All right. Next thing we do is to say, well, we can't use 6 now because that's already been used. The next person up is 40. They're ranked 7th. Then we go 8, 9, 10. Hope that makes sense. We do exactly the same with rank B as well. So if you look at column B, attractiveness score, we find the lowest attractiveness score here, which was 3, and then we rank them 1, and then effectively just go through the rest of them in exactly the same way that we did for the ranking in A. The only problem that you can ever have with those really, well, 2 problems really. One, you kind of make a mistake and you forget one, so it's a good idea to kind of score them off as you're going along. The other thing is when you have 2 that are the same, it's not particularly difficult, but it's just something to bear in mind. Next thing you need to do is the difference between the ranks of A and B. So it's a simple case of taking 2.5 from 10 in this particular case, and then going down that and doing exactly the same sum the whole way down. So 9 from 5.5, 5 from 9, etc. And you end up with the differences between rank and B as your column D. Next thing, we need to square these. Okay, so 7.5 squared is 56.25, minus 3.5 becomes 12.25. You notice there that the negative sign gets taken out when you square it. And we go down the whole way through that again. Last thing that we do with this table, we're done with the table after this, is we just simply need to add up the square of the differences. Yeah, we end up with 261. Right, what do we do next then? We're going to have to do a little bit more information. We're going to have to do a little bit more with this, I should say, with this information. And we're going to apply this to this rather scary looking formula here. I say it's scary, but actually it's not if you just break it down into its contingent parts. We already know this, don't we? 261, because this is the sum of d squared, which we've got here. Okay, and we're going to times that, multiply it up by 6, and we're going to divide it by n times n squared minus 1. We already know n's 10, isn't it? We've got that from there. So let's plug this into this equation anyway and see what we end up doing. The easiest way I find with this is to simply ignore the 1 minus, okay, until the very end. Just deal with all this stuff first of all, and then that bit gets sorted out at the end. Hopefully you'll see what I mean. Right, so we've got 6 times 261 divided by 10 times 100 minus 1. Let's simplify that. That ends up as 1566 divided by 990. We do that sum, we end up with 1.582. Then we bring in our 1 minus 1.582 equals 0.582. So what we have done now is we have found out our calculated statistic. That is rho. Right, that's all very well, but it doesn't tell us anything unless we plug it into our critical value table. Critical value table is very often where students have a bit of a problem, but if I just very quickly go through this with you, hopefully you'll understand it. I don't think it's too hard really. All we need to remember is that we are looking at a two-tailed test, okay, a two-tailed hypothesis. So we're going to ignore this row altogether because that's about one-tailed test, and we're just going to look at that row instead. So the level of significance for a two-tailed test, 0.1, 0.05, it's psychology. We always use 0.05 unless we're told otherwise. Okay, so we're going to use that row and we're going to use that column. What does n equal? Well, n equals 10, doesn't it? Because that was the number of participants. 0.05 row, 10. 0.648 is our critical figure, our critical value for row. And underneath that, it tells us a little bit more. It says the observed value of row must be equal to or greater than the critical value in this table for significance to be shown. So in this particular case, we can just ignore the minus figure. That doesn't really matter. It only comes into it if we had a one-tailed hypothesis, which we don't in this particular situation. Well, is 0.582 equal to or greater than 0.648? No, it's less than it, isn't it? Okay, so that's going to tell us straight away that we do not have significant results here. So let's go through this. It says, can you accept the alternative hypothesis? No, we can't do that because the calculated value of rho is less than the critical value of 0.648 for the results to have been significant at the 0.05 level. Okay, so this is a non-significant result. And how do we write that as a significant statement? Just like this, dead easy really. Rho equals minus 0.582. That was our calculator score. N equals 10. We know that. P, instead of the little arrow thing pointing in the other direction as it normally would, is pointing in this direction, which suggests that P equals greater than 0.05. So in other words, we will reject the alternative hypothesis and accept the null hypothesis. So after all that, there doesn't seem to be a relationship between age and attractiveness. Okay, hopefully that was useful to you. Do stop and start it, go back and forth on this video, and hopefully it will make a bit of sense. Thanks.